We are now ready to actually use our model. We are now going to train our model locally and then in a distributed manner using the Google Cloud ML engine. Let's first start by just trying this model out on a local sample and making sure that it works fine. The important bit here is that the training data as well as the validation data that we are going to feed into this particular run are going to be a small subset. These are not the large files that we wrote into cloud storage. Rather, these are the much smaller files that we saved to the local persistent disk of our virtual machine. So let's go ahead and kick this off on the local data. We specify 100 epochs. Remember that one epoch is one complete pass through the training data. The job runs. We scroll down and search for the RMSE, which is now at 7.13. Once again, this is on a subset of the training data that we have saved locally. The process runs through to completion, and at the end of it, we have a saved model. This saved model resides on a local directory on our virtual machine. Let's go ahead and call ls and confirm that it does indeed exist in that servo directory. Yes, it does. So we can now go ahead and invoke this model for prediction. So we're going to create a small JSON file. This JSON file will consist of all of the values for the predictors, that is the X variables. Let's go ahead and pass this JSON file into our model, making use of the local prediction mode of Cloud ML Engine. So you can see gcloud ML Engine local predict. This is followed by the model directory as well as the JSON file that we just created. TensorFlow and Cloud ML Engine will work together. Our model will be invoked on this JSON data, and the return value from our program is the predicted fare for that particular instance. In this case, we only have the one instance which we passed in, and so the one predicted value is 18.03. That's the predicted fare for the trip that we encoded in our JSON. We've now reassured ourselves that our model at least works. We've used the local training and prediction services. Let's go ahead and now train on the cloud. This requires us to invoke gcloud ML engine once again, but this time with the jobs submit training commands. This is now going to carry out distributed training on the cloud. And so we are going to have to tell the Cloud ML engine where to find our model package. This is why we need to specify a package path. Notice that this package path is a directory location which contains the model that we've just saved. Notice that this directory location is not on the cloud storage bucket. This is a local directory within the VM that is running our data lab IDE. gcloud ML engine is smart enough to pick up the code from there, create a package, and go ahead and run the distributed training path. As before, we'll need to specify paths for the training and the validation data, but there's something different about these paths this time around. We are now going to carry out the training and the validation on much larger subsets of data which reside in cloud storage buckets. These are the sharded files which we wrote out from our data flow job. So let's go ahead and kick off our training process, our training job. This gets submitted successfully. We can now switch back over to the web console in order to monitor it. So let's do exactly that. We now go back and search for ML engine, and there we click on jobs. Once we do so, we'll find a list of all of the pending jobs that we have submitted. In this current instance, we have one running job and one successfully completed job. Let's click on the running job. You can see right now that it's still preparing the job for submission, that is starting to run 23 seconds in. This job actually takes a really long time. It takes 18 minutes and 55 seconds to complete the distributed training process. And keep in mind that this is still only with a fraction of the data available to us. So you can see that making use of a distributed training service like Cloud ML Engine is really pretty important. Once the job has successfully completed, we can examine the logs, and there, buried deep within the logs, we can find the RMSE, which is 8.79. This is still a much lower RMSE than we were obtaining at the start of our process, but even so, keep in mind that this is still only with a very small amount of training data. And what's more, this is the RMSE that we get even before we carry out any hyperparameter tuning. All that we've done at this point is make use of a deep and wide model. Let's turn back now to the model code provided by Google, and we see there that the author discusses hyperparameter tuning at this point. We are about to examine the code, the Python code that's actually used to carry out this hyperparameter tuning, although we will not actually execute it because it just takes a really long time and quite a bit of money on the Google Cloud. But before we examine the code, let's parse what the author has to say about the hyperparameter tuning here. By using Cloud ML Engine with hyperparameter tuning to try out different combinations of the training batch size, the number of buckets, and the number of hidden units, the author was able to bring the RMSE down from 8.3 to about 5, which is a huge improvement in the model performance. So clearly, hyperparameter tuning is an important part of getting real production level improvements in machine learning models. And this really corresponds to the final step of our exploration of TensorFlow with Cloud ML Engine. This hyperparameter tuning, which we are not actually going to perform ourselves, is going to involve specifying a configuration file that is called hyperparam.yaml. YAML is a common file format for config files, and it is an acronym for yet another markup language. We've already discussed hyperparameters at length in this course. We understand that these are variables which define the training process, properties such as the number of training steps, the batch size, the number of neurons in the hidden layers. All of these are hyperparameters. The great benefit that we get by using a config YAML file along with Cloud MLE is that the Cloud ML engine does a smart job of picking specific values of the different hyperparameters. Let's say we were not performing hyperparameter tuning using the ML engine, it's quite likely that we would have hard coded the values of at least some of these configuration properties. However, in order to get the full benefit of hyperparameter tuning, we typically will define command line arguments within our main trainer model for each of the tuned hyperparameters, and we will then assign values to those command line arguments from the YAML file, which is passed in as a config argument. That job, that process of parsing the configuration YAML file and passing the appropriate values to our trainer package, that is something that Cloud ML Engine takes care of for us.